So hello uh to this lesson, and this happens to be our third lesson in our study of mathematical biology 2. So in this lesson we'll be talking about harvesting in population models. So note that in our first lesson we talked about the multi-chain growth model. In our second lesson we talked about the logistic growth model, and now we'll be shifting our focus to harvesting in population models. So I'm Guido Randolph, a final year student of mathematics at University, and I'll be taking you through this lesson. So let's take some introduction. So among the most important concerns in biology ecology, in population ecology, is the effect of harvesting a natural population. So when we have a natural population and we want to harvest some, so for instance, when we have fishes, we do harvest some, right? When you have a poultry farm, we do take some out of it by selling it or doing a lot of things to it. So we want to study the effects of doing these things in the natural population. So harvesting can represent reduction of the members of the population due to hunting, which in fact removes individuals from the population. So harvesting always represents a reduction in the population, because you have a population, you are taking some out of it. So we wish to study the effect on a population model of the removal of members of the population at a specified rate. Okay, so we have a population and we want to take some out of it. So we would want to know the effect of taking this number of the population at a specified rate to know whether the population will go into extinction or not. So we would always want to study it, because if we should just remove the members anyhow, it could be that at a point in time the population will go into extinction. So you want to have a mathematical model which will be able to help us to make such important decisions when it comes to removing some of the members of the population. Okay, and that's what the harvesting model seeks to address. So if a population modeled by differential equation f prime equals f of p is subject to a harvest at a rate of ht members per unit time for some given function h of t, then the harvested population is modeled by the differential equation p of p prime is equal to f of p minus h of t. Okay, so this is the population and this is what we are taking out of it. So we have two types of harvesting. We have the constant yield harvesting and a constant effort harvesting. So we talk about what the two of them mean, and we will talk about the equations for them and also analyze their equations. Okay, so this is basically what we are talking about. So far we've talked about two models for predicting the size of the population, right? So we talked about the Malthusian growth model, which was of the form. So we had something like this. Then we talked about the logistic growth model, which was of the form. Alright, so you can see these two populations here. They are used to estimate the population size of a species, right? Okay, so right now what you're interested in is that what if there is harvesting in a population? We have a population where we harvest some from it. Okay, we want to study the effect of the harvesting on it. So that's the reason we are studying the harvesting population model. So we are studying the effect on the removal of some of the members from the population. Okay, so that's the reason why you can see that this here is f p prime is equal to f of p, right? The equations here are all in this form, but now we want to study when there is a factor minus h of t introduced to it. Okay, So that's what you're coming to study here, and that's the harvesting. So we have two types of it: the constant yield harvesting and the constant effort harvesting. Okay, so let's take the first one, the constant yield harvesting. So if the function h of t that we introduce, so I think the constant we introduced was h of t, right? So if the constant h of t that we introduced is a constant h, so that members are removed at the constant rate of h per unit time, then the model is given by p prime is equal to f of p minus h. Okay, so this type of harvesting is called the constant rate or constant yield harvesting. Okay, so this is what the constant yield harvesting means. So with this particular kind of harvesting, we have a specified number that we are supposed to harvest from the population. So when we have a specified number that we are supposed to take away from the population, then that kind of harvesting is what we call the constant yield harvesting. So it says it arises when the quota is specified, for example, through permit. So maybe you go for permit and you've been told to maybe take 10 of the species you are trying to harvest every week. So you can say that you have a constant number that you do, right? So when a constant number is specified, when the h of t, the one you're harvesting, is a constant h, then we see that we have the constant yield harvesting. And with that one, our model becomes p prime is equal to f of p minus h, right? Okay. So for instance, if our population is governed by a logistic equation, then the model with constant yield harvesting will be given by this equation one here. So you can see that this is the p prime, this is our f of p, and this is minus h. Okay, but just that now the equation is modeled by the logistic equation. So the f of p is rp times 1 minus p over k, then minus h. So let's take a critical look at this equation here, this model here, because we are coming to go through the qualitative analysis of it. Okay, so now let's walk through the qualitative analysis of it. So we have the PDT is equal to RP times 1 minus P over K minus H. So this alone is the logistic growth model. And this here is the constant yield harvesting rate here. Okay, so we have to analyze it qualitatively. So the first thing that we do is to find fixed points. And to find fixed points, we put the derivative to 0. So we put the PDT to 0. Then we know that we are going to get this equation here. Then when we multiply through by the RP, we get RP minus RP squared over K minus H equals 0. Then we can decide to multiply through by negative 1. Alright, so we multiply this through by negative 1 to obtain this here. So when we do that, we will get RP squared over K minus RP plus H equals 0. Then when we get here, we can decide to divide and multiply through by K. Sorry, let me go back to. So we can decide to multiply through by K. So when you multiply through by K, you're going to get RP squared minus RKP plus HK equals 0. Then we decide to divide through by R. So when you divide through by R, we're going to get P squared minus KP plus HKR over R equals 0. And we call this equation 2. And you know equation 2 is a quadratic equation, right? So comparing equation 2 to the quadratic equation, ax squared plus bx plus c equals 0, it implies that a is 1. Can you see that when you compare these two? And it implies that b is minus k, and it implies that c is hk over r. So you know, to find the root of this quadratic equation, we use a quadratic formula, which is given by minus b plus or minus root of b squared minus 4ac over 2a. So this is our b, this is our a, this is our c. We just make substitution into the quadratic formula. And this will give us p star will be equal to k plus or minus root of k squared minus 4hk over r all over 2. I hope you get that. When we just make substitution into this, we'll get this. So this happens to be our fixed point. Okay, we are going to have two of it. So because one will be plus and one will be minus. Okay, so we have these two fixed points. PL, we are calling the first one PL to be equal to k minus root of k squared minus 4hk over r all over 2. And this will be our PU, which should be equal to k plus root of k squared minus 4hk over r all over 2. So this happens to be our two fixed points, right? And now we have to analyze these two fixed points to know when they are stable and when they are not. Okay, so first of all, you know, we have root of k squared minus 4hk over r, and you realize that as to whether we get complex root or real root is going to depend on this factor here. Okay, so you realize that if we only get real root if what we have here, which is the k squared minus 4hk over r, is greater than or equal to 0. If this thing is greater than or equal to 0, then we have real roots. Or when our h is less than or equal to rk over 4, that is when we have real roots. Okay, so the reason why this is the same as this is, let's try this and see. So you see we have k squared minus 4hk over r is greater than or equal to 0. So we can decide to multiply through by r. We'll get k squared r minus 4hk greater than or equal to 0. This is the same as k squared r greater than or equal to 4hk. When we divide through by k and 4, we will get kr over 4 greater than or equal to h. And this can be written as h less than or equal to kr on 4. So that's the reason why this term here is the same as this. Okay, and this term here what we call the critical harvesting rate. So with the fixed points that we had, we only get real roots provided k squared minus 4hk over r is greater than or equal to 0, or h is less than or equal to rk on 4. So now let's take the analysis of the qualitative solution. So we get complex root when k squared minus 4hk over r is less than 0, or when h is greater than rk on 4. I hope you understand that. So if this thing here is less than 0, then we'll get complex root. So 1, if h is greater than rk on 4, then both roots are complex. And when both roots are complex, what it means is that s prime of t is greater than 0 for all x. And so every solution crashes, hitting 0 in finite time. And if every solution reaches 0 in finite time, then we consider the system to have collapsed. Okay, so that means that in a case where our h is greater than rk on 4, we are going to have complex roots, and as a result of that, the system is going to collapse. So that means that in harvesting, we wouldn't want our h to be greater than rk on 4. Do you get it? Okay, so when 0 is between when h is between 0 and rk on 4, okay, then there are two equilibria. So we have the pl, which we have already found, which increases from 0 to k on 2 as h increases from 0 to rk on 4. And we have pu, which decreases from k to k on 2 as h increases. So what we say, this can be a diagram that we can use to represent that. Okay, so then we have 0, k on 2, and k, and there's rk on 4. So we have our fixed point pl here, our fixed point pu here. So our fixed point pl increases from 0 to k on 2. So it increases from 0 to k on 2 as H increases from 0 to RK on 4. Okay. In PU, which decreases from K to K on 2 as H increases. Okay. So you see with the PU, we move this way. So as a result of that, PL is always unstable. Our fixed point PL is always unstable, and our fixed point PU is asymptotically stable. So that's it with the constant effort harvesting. So with the constant effort harvesting, with the constant yield harvesting that we just discussed, what you can infer from this, that it will tell you that in order to make sure that the population does not go into extinction, when you're harvesting, your H, that's the constant that you harvest, should be between 0 to RK on 4. It shouldn't exceed RK on 4. When it exceeds RK on 4, we are going to have complex roots, which will make the population go into extinction. Okay. Alright, so thank you very much on that one. So now let's go to the constant effort harvesting. That one is a bit different from the constant yield harvesting. You with the constant yield harvesting, you go for a permit and they tell you a specified number that you're supposed to harvest at a particular rate, maybe per unit time. So maybe every 10 days you can harvest 10. So that means it's going to be a constant. Every 10 days you go for 10 of the animals that you are harvesting. Okay. But with the constant effort harvesting, the concept is different. So it is clearly necessary to develop an ecological acceptable strategy for harvesting any renewable resource, be it animals, fish, plants, etc. So we usually want the maximum sustainable yield with maximum effort. Okay. So what the constant effort harvesting does is that the amount of animals that you harvest is proportional to the effort you put in. So, for instance, let's take an example in fishing. For instance, when it comes to fishing, the number of fishes you harvest is proportional to the effort that you put in. So, the number of nets, how wide you will go into the sea, and a whole lot of things. Okay, so this is what we term as constant effort harvesting. So, with the constant effort harvesting, the yield that you get is proportional to the effort that you put in. So without this one, no particular number is specified for you. The number you get is based on the effort you put in place. Okay. So that's what we term as the constant effort harvesting. So a basic model which consists of the logistic model in which the mortality rate is enhanced as a result of harvesting by a term linearly proportional to P is given by what we can have here. So you could see that in the case of the constant yield harvesting, we have just H here, right? And that H was a constant. But with the constant effort harvesting, our effort is proportional to the population that we are going to harvest. Okay. So this is going to be the model for the constant effort harvesting. So with this type of harvesting, we call it the proportional or constant effort harvesting. And here our R, K, and E are positive constants. And EP is the harvesting yield per unit time with E, a measure of effort expended. Okay. So now let's look at the qualitative solution for that one. So we have the equation, the model to be dPdt is equal to RP times 1 minus P over K minus EP. So first of all, we have to find the fixed point since we are solving it qualitatively. So we set dPdt to 0. And that will give us R times P all times 1 minus P over K minus EP equals 0. So when you multiply through by the RP, we get RP minus RP squared over K minus EP equals 0. And when we get this, you can see that we have P to be a factor in all of them. So we can factorize P out. And we get P multiplying R minus RP over K minus E equals 0. And this means P equals 0 or R minus RP over K minus E equals 0. And when we solve for P from this, we are going to get P will be equal to K multiplying R minus E over R. Okay, so we had P equals 0, and we had P equals K multiplying R minus E over R. So the two fixed points are 0 and Q over R times R minus E. So our fixed point 0 is always unstable, and our fixed point um, K over R or multiplying R minus E is asymptotically stable for 0 for E, which lies between 0 to R. Okay, so know that the fixed point 0 is always unstable, and the fixed point K over R times R minus E um asymptotically stable. So the other ones we are going to analyze it. Okay, so for a given effort E, the yield is given by Y of E is equal to EP, right? Where P is the non-zero equilibrium point. And you know, the non-zero equilibrium point, we found it to be Q over R times R minus E. So that means that the yield is given by Y of E equals E times the non-zero fixed point. So K R minus E all over R. Okay, so this is the yield. Okay, so let's take examples to explain what you've done and you really get the concept. Okay, so the first question says a population of fish that would otherwise grow according to the logistic law is fished at constant rate kill en, where kill is the catchability coefficient. The first part says that we should show that the steady state in the presence of fishing is given by this. The second one says we should find the steady state yield effort relationship. And the C says we should find the maximum sustainable yield. The maximum sustainable yield. Okay. Alright, then after that, so this is going to be on the constant effort harvesting. Then question 2 says a population of sandhill cranes has been modeled by a logistic equation with carrying capacity of 194,600 members and intrinsic growth rate 0.0987 per year. We have to find the critical harvest rate for which constant yield harvesting will drive the population to extinction. And we have to find the equilibrium population size under constant yield harvesting of 3,000 birds per year. So this one is under the constant yield harvesting. Okay, so we are going to solve all of them for you. So the question 1, this is the logistic law which was given, okay, and the fish, they are being fished at a constant rate of KEN, right? So when we introduce the harvesting into the logistic model, we are going to have Rn times 1 minus n over k minus QEN, where this is the term that the harvesting term that we added to it. Okay, so the first question says that we should show that the steady state in the presence of the fishing is given by this equation here. So for the steady state, we have to find a fixed point of our model, right? So we set the derivative to 0, that's m prime to 0, and we will get r times n all multiply 1 minus n over k minus q e n equals 0. When we multiply through by the rn, we'll get rn minus rn squared over k minus QEN equals 0. So we have n in both sides, all of them, right? So we can factorize n out. And when we factorize n out, we get n multiplying r minus Rn over k minus QE equals 0. And this means n is 0, or r minus Rn over k minus QE equals 0. So we seek to make n a subject here. So we will have, by multiplying through by sending Rn over k to the right hand side, we have r minus QE will be equal to Rn on k. We multiply through by k to get this, and we divide through by r to get this. So we have shown that n star, which is the steady state, is given by k 1 minus QE on r. I hope you understand, right? So this was very simple for us to find out. Okay, so that's it. We have shown that here. Then the next question says we should find a steady state yield effort relationship. That one is very simple. Do you remember here I said for a given effort E, the yield is given by Y of E equals EP, right? Where the P is the steady state that we just found, we just showed, okay? And the E is the rate. In this question, the rate was QE, QE before we have our N. Okay, so that means that with this question, for the steady state yield effort, Y of E will be equal to U key, E E times Q, then times N star, when N star happens to be the steady state that we just found. Okay, so when we make substitution, we will get Q times EK, or multiply 1 minus QE over R. And that's it. That's very simple. Okay. In the C part of the question says we should find the maximum sustainable yield. So to find the maximum sustainable yield, we know that this is the relation that we had for the yield effort, right? The yield effort relationship. So at the maximum sustainable yield, dy of EDE is equal to 0. That's what we have here will be 0 when we differentiate with respect to E. So, but from B, y of E is equal to Q times E times K all times this. So when we multiply through by the Q times E times K, we'll get Q times E times K minus Q squared E squared times Q over R. So when we find the first derivative of this function here with respect to E, we'll get Q times K minus 2Q squared times E times K on over R, right? Then to find a point, we set this equation to 0. So when we set it to 0, we'll get QK will be equal to 0, or the whole of this equals 0. So that's what you can see here. And this place will give us 0, and here we find E. So we have 1 minus 2 times Q times E over R equals 0. So when we find E, we can multiply through by R. So we get R minus 2QE will be equal to 0. Then this will give us R will be equal to 2 times Q times E, and E will be equal to R over 2Q. Right? So that means that at the maximum sustainable yield, the effort given should be R over 2 times Q. Okay, so now let's see the sustainable yield that this effort is going to produce, or say, okay, so to get that, we take this E equals R over 2Q and we put it into this relation. Okay, and that's going to give us the maximum sustainable yield. Okay, so the maximum sustainable yield will be equal to K times E, but now E is given by R over 2 K. Then we have our K times 1 minus K over so we have our E R. Okay, so we just make substitution into this relation as I said. So when we take this one, this K will cancel this K. We're going to get RQ on 2, and here too this K will cancel this K, this R cancel this R, and we just get 1 minus half, which will give us half. So we get RK on 2 times half, which will give us RK on 4. And this happens to be the maximum sustainable yield. Okay, so that's the solution for the first part of the question. The question that we had, so question 1. Now let's go to question 2. So question 2 says that a population of sandhill cranes has been modeled by a logistic equation with carrying capacity of 194,600 members in intrinsic growth rate 0.0987 per year. We have to find the critical harvest rate. The critical harvest rate for which the constant yield harvesting will drive the population to extinction. And we have to find the equilibrium population size and the constant yield harvesting of 3,000 birds per year. Okay, so let's solve that question. So from the question 2, our carrying capacity was given to be 194,600, and the intrinsic growth rate is given to be 0.0987. So we have to find a critical harvesting rate which will drive the population into extinction, right? Okay. So the population will go into extinction when H is greater than RK on 4. So to find the critical harvesting rate, it is given by H equals RK on 4. And we just make substitution. So our H is 0.0987 times our K, which is 194,600 all over 4. And when you compute this, you get this, and we can round this to the nearest whole number to be 4,802. So that means that any number above this will drive the population into extinction. So that's going to be the critical population, um, the harvesting rate, critical harvesting rate. Okay, any number above this will drive the population into extinction. So the B part says you find the equilibrium population size and a constant yield harvesting of 3,000 birds per year. So before that we found the two fixed points for the constant yield harvesting, and we said that this was the one which was stable, asymptotically stable. So we use this formula to find the equilibrium population size and not the constant yield harvesting of 3,000 birds per year. So we know what our carrying capacity is. We've been given our H to be 3,000 and our R is 0.0987. So we just make substitution into the formula. We get something like this, which when we compute, we get 156,901.983, which we can round to 156,902. So this is going to be the equilibrium population size and a constant yield harvesting of 3,000 birds per year. Okay, so that's it with the harvesting in population models. So it helps you to know some decisions to take before harvesting a population, so that population does not go into extinction. Okay, all right. So thank you very much for following. If you didn't get anything, you can always go back and watch the videos. So in our next lesson, that's lesson 4, we'll talk about non-dimensionalization. Okay, so thank you very much and see you in the next lesson.